Good afternoon, Sir Chen. Are we audible to you, sir?
Oh, yes. Good afternoon. Yeah. Can you hear me? Uh,
Yes, sir, we can. Could
okay,
you please
good.
try to find out that either you are able to share the screen?
Okay, I'm sharing the screen now.
Sir, it means that all the options are present towards you or on your screen, right?
Yes, yes, yeah. I think,
Thank you so much.
yes.
Yes, sir, here the
Yes,
screen is visible.
you can see the screen now. Okay, good.
Yes, sir. The screen is visible and
Okay, good.
hope so the participants can easily also screen. Yes, sir. On
Okay,
both the screens are visible.
okay,
Thank you
good.
so much, sir.
Okay, thank you.
Okay, Professor Chen.
Oh, yes.
Yes, thank you very much for your time. So, with this, we will be beginning with lecture number 4 on supervised machine learning methods, part 2, under the course Applied Biomedical AI. So, over to you, sir. Please start your lecture.
Okay, thank you. Okay, so today is our fourth lecture. Starting from fifth lecture, we are going to have a practical session after the lecture time. So it probably will be one practical session every after every 3 lectures. So it means that the fifth lecture and then the eighth and so on so forth. Okay. So today we are going to continue our study of supervised machine learning method. This is the part 2 of the series of supervised machine learning methods. Okay. So now we need to mention a little bit about what is a supervised machine learning. Essentially, we know that in order to train an AI, right, we need to supply the AI with some data, training data, right? So this training data may be in the form of certain labels, just like patient, healthy controls, positive and negative, inhibitors and non-inhibitors, and so on and so forth. So that means that when we supply data to AI, we actually have some label on the data, either positive, negative, inhibitor, non-inhibitor, and so on and so forth. These labeled data uh, are the ones we want to supervise a machine learning or any other AI method that can actually be able to distinguish. So this type of training process is called supervised training process, and the machine learning model developed this way is called the supervised machine learning method. Okay. Okay, today we are going to study 3 methods: support vector machine, decision tree, and the random forest. Okay, so in these 3 methods, we want to further illustrate how we can develop a mathematical relationship. That means we want to be able to draw a borderline, define a zone for whatever I just mentioned, right? The positive zone or negative zone, inhibitor zone or non-inhibitor zone, and so on and so forth. These 3 methods actually illustrate different strategies, the strategies that are different from the ones we studied in part 1. Okay. We first look at support vector machines method. Okay. In this method, the task is again the same. We wish to be able to draw a border line that separates the positive from the negative samples, like this one. This example shows the essentially you have the green samples representing people wish to play tennis, and also you have red sample they do not, right? In determining the borderline, so we are here for simplicity. Again, we focus on straight lines, linear borderlines. In defining linear borderlines, we know in this particular simple case, we know that we can actually draw many different straight lines to perfectly separate the samples. Of course, the perfect here doesn't mean the best one. It means that we can clearly separate the samples. Now the question is, there are so many possible straight lines to separate the samples. What is the most suitable one? What is the best solution for the borderline? So the method that determine the best solution is called support vector machines. Okay. So let us consider the case, right? So you can draw any line to separate the samples here, right? So how can we define some line that actually be the best borderline to separate the samples? This is a problem, just like we want to separate opposing troops. So we want to have a ceasefire line, borderline to separate the opposing troops. What is the fairest way? What is a fair way to define the borderline? Of course, that depends on the position of the opposing troops, right? So essentially, the borderline must be such that it is fair to both sides. Ideally, the border should be in the middle between the opposing troops, right? So this is the strategy exactly adopted by support vector machines. Okay. In defining this kind of ceasefire border, definitely we want to know the position of the troops. And we based on the position of the troops, you can define a fair border, right? So it is the same thing here for a support vector machines. We first identify the front line samples, the sample that are closest to the other side. These samples are called support vector. Remember that each dot here represents a vector, right? A vector is a position in this two-dimensional space, or we can generalize to a n-dimensional, high-dimensional space, right? So each dot here is a vector. We want to select those vectors that are closest to the other side. These vectors are called support vector. A support vector machines method, the task of a support vector machine method, or we can use SVM for short, right? So the task of SVM is to find the borderline based on the position of support vectors. Okay. So this requires us to determine which equation support vectors must obey. So for simplicity, we can first assume support vectors are all along a particular line. Of course, in reality, it may not be a perfect line, but we can always do this kind of mapping in the n-dimensional space to find a certain lightened space in which the support vectors are aligned along a straight line. So this can be done as will be discussed later on. Okay, so for example, for this particular line, the dashed line of support vectors on class 2, for instance, and we can, because it is a straight line, of course, it must obey certain linear equation. Let's write down it this way. And then we can assume that another side, right, on class 1, it is also we can also assume it obeys some equation which is differ by a certain distance to separate the samples. The distance can be defined by this value. The distance called m. This value. And then the w is the width of the linear equation. So essentially, the absolute value of the width defines the separation of the two dashed lines. So this way, we have three equations: support vector equation for class 2, support vector equation for class 1, and also a equation for the borderline, the border that is fair to both sides. So this forms the foundation equations of the support vectors and also the borderline. Of course, there's this question, how do we determine all those parameters, the W's and the B values? Without determining those, we cannot really determine the essentially the borderline. So the equation can be determined by maximizing the separation, because we certainly we can select different vectors to be support vectors. By selecting different vectors, you actually define different the lines, right? The support vector lines. So we can actually adjust the parameters by which we also, that means that we also select the different support vectors in such a way that we want to maximizing the separation between one class of samples and the other class of samples. And we can do this not only in sample space, but also in some latent high dimensional space. We can change it to different space in order to find such a good separation. So here is an illustration. If we use the nonlinear function, we can actually find a nonlinear borderlines. Here is an illustration of support vector machine training process in which they adjust the parameters until, and also they select different support vectors until they find that the borderline that is fair to both sides. Okay, so this is a graphic illustration of this process. Now there's this question: how can we have initially we have a nonlinear borderline, nonlinear separation, or the irregular separation of the samples? How can we find a so-called latent space in which the borderline becomes a simple straight lines? There must be some nonlinear function to help us to achieve that. So what is that nonlinear function? So in this way, we must use a trick called kernel trick. So essentially, we use multiplication functions between two variables. And also, we remember that we have the parameters that can actually help us to adjust the choice of the vectors, the support vectors, and also the parameters of the linear equation in that latent space. So mathematically it becomes complicated. So I think for us in this lecture that really covers the biomedical applications, we do not want to devote too much time to actually dig into the mathematics of the theory. Rather, you just need to know that we have some sort of multiplication functions that can called the kernel function that can help us to do this trick of nonlinear transformation. So on the bottom, you see an example of this linear equation. It's simply the dot product between two vectors with the square value. So this is one example of the kernel function that help us to do this nonlinear transformation. So this is the first method of today, support vector machines method. Now we come to the second method. It is called decision tree. Remember in our previous one of our previous lectures, we talk about how we can develop a mathematical relationship. Remember that we define the rules to actually to separate the samples. So decision tree, again, use this kind of strategy. We use rule-based method to define zones. So it is still a workable strategy we want to further look into, but we do not want to uh, develop so many if statements as a rule-based method. Rather, we still rely on mathematics. Okay, so we start with this decision tree architecture. Okay, so we begin with a first situation on the top. We have a sample. For instance, we have sample. We want to decide whether this particular sample want certain action. For instance, want to go outside. And then we can have certain situation to determine whether it is worth to go outside or not. For instance, if it is a rainy or sunny day and so on and so forth. So in this case, this is also the case we frequently encounter when we decide when we make our own decision about certain actions. We actually make decisions based on the current situations. If under this situation we do this way, if the other situation we do an alternative way, right? So we have this situation, we start from A. If it is on one condition, we go to the left-hand side, go to the situation B, and then again, based on the situation encountered in B, we may further go to either to the D or to the E, and then we again, depending on the situation. So we are going to look at a specific example later on, but here I just mentioned that a decision tree is simply a one decision followed another, branch out type of approach. This is the way. Now we look at a specific example, how a decision tree method look like. Just as I just mentioned that we begin with the weather situation. It could be sunny, overcast, or rainy day. So depending on which type of day, and we may decide to go three different ways. So we want to do some activity. Of course, if the weather is not rainy and it's also not too hot, we can immediately decide that this is the day we want to take the action. So it reach the final class, yes class. Okay. If alternatively it is either sunny or rainy day, we have to further look into the weather. For instance, in the rainy day, if it is windy, we decide not really to take the action. If it is not windy, it is tolerable, we may decide to proceed with the action. On the other hand, if it is a sunny day and we want to look at the further into the weather to see if it is we can tolerate the heat. If it is too humid, we may decide not to take the action, right? If it is not too humid, we may deem it is tolerable, we do the action. So this is an example of the decision tree type of AI. But here, what we see here, it is all this kind of if and then action. Certainly, this is not the way to actually develop a decision tree algorithm. What is a better way to do that? So this comes to the problem, how we define different zones. So essentially, when we define multiple zones, different multiple zones, essentially we draw lines cross each other, and this way we can easily separate one zone from another, and based on the the specific character of each zone, we can decide where which direction to draw the lines. This way we can easily separate many zones, just like in a particular country, and they have multiple states. They have a borderline to separate. For instance, in the United States, some states actually has this straight line border, just as if, right? They just draw draw some lines on a map, and to separate the zones of one state from another. So this is just the kind of example. So we want to introduce this type of approach to a decision tree algorithm. Okay, let's consider this situation. So we have in this situation, it deals with the emails. So we have emails, many emails of different length. That means a different number of words, and also it has the emails are directed to different recipients. So we want to figure out the so as the figure on the left side shows that, so each dot represents a particular email. You can see some emails are quite long. They are on the top side. Some emails are short. And then the color of the emails represents essentially they represents whether it is a spam or the normal email. We want to, essentially our task is to screen, to block the spam emails. So we can see that we could somehow separate or actually pick out many red dots based on the definition of a particular straight line, the horizontal line here, right? So, or in another word, we have this kind of decision tree. If the email length, so we start from the length of the email. If the email length is smaller than certain value, because it is short, normally spam mail could be short, we can simply define those short emails as spam. In this way, we only have one error. But for those deemed non-spam, the normal emails, unfortunately, it has a large number of essentially the wrong actually they are spam mails, right? They are the error ones. So we know that a one level type of decision tree is not good enough. That means if we only use one straight line for separating spam and non-spam mail is not the best way. So what can we do with this decision tree strategy? How can we improve the performance of our decision tree? Okay. Okay, so one solution is that we define a different decision tree. Instead of using horizontal lines, for instance, why not we try a vertical line? So this is one example, right? We have this vertical line. Remember that a vertical line actually uh, uh, separate emails not in terms of the length of emails, but rather in terms of whether or not they are new recipients, uh, what kind of recipients are. So this way, we have, remember that we have horizontal decision tree, horizontal line decision tree in the previous the page. Now we have a new decision tree based on the new recipients. And then we can see that if we choose a cutoff of 2.3, we can have we have a separation of spam and non-spam. Unfortunately, again, with large errors, 4 errors for spam, 11 errors for the non-spam. So we can see that both decision trees have errors. So how can we do with this situation? So now we need to try to combine both. So obviously we know the second one is actually worse. So now the question is, can we develop a deeper decision tree? Okay, so now we add a second level of a decision tree. By second level, we mean that we draw another line, another straight line. So this is just essentially the same strategy I mentioned before, right? We draw multiple lines to define multiple zones. So this way, obviously, we know that one simple line of 2 zones is not good enough. Why not we draw? Essentially, based on what we see from our eyes, we know that there must be multiple zones, right? So we add a second horizontal line. So this horizontal line becomes the second level of decision trees, a deeper level of decision trees. In this case, horizontal line is still with respect to the length of the email. So now we have a new cutoff of 4. If the length is greater than 4, we deem it as a spam. If not, we deem it as normal. In this way, you can see there are still errors, particularly for the non-spam. So that means we have to draw another line, add another line. So this way, we may combine the vertical lines. So this is the third line, the vertical line, with respect to the new recipients. So this way, if we draw a third line, that means we introduce another level of decision tree. We go a deeper level. So the third level, in this level, we actually look into the new recipients dimension of the email, and then we can again choose a particular cutoff to actually, so essentially it is illustratively a value of 1. Essentially, we can actually separate the spam and non-spam with a very small error now. You can see that altogether, at each step, the error rate becomes just 1 or 0 error. So now we have a decision tree, a deeper level of decision tree with quite uh, uh, a good classification power, essentially. So we can have a more and more complex, this way we can develop more and more complex decision trees. So this is a illustrative example of decision trees that separate lung cancer patients from healthy persons. You can see that it is based on, again, in this situation, it is based on medical examination biomarkers. It can be genetic biomarkers or biomarkers of other clinical examinations. So essentially, this is just illustration. Okay. So far, we introduced the two methods. Okay. Now we look into a third method called random forest. So this method is by far the most powerful method. So it is based on a decision tree type of strategy, and but rather it has the power to deal with a smaller number of samples. Remember that in medical studies, frequently we have a smaller set of some patient samples, maybe several dozen, or maybe a few hundred. So that's the frequently case. Actually, a colleague of mine actually wanted to collect essentially the blood and also the blood, the urine, and also the essentially the stool samples from the colon cancer patients. So he wanted to have both the metagenomic and also the genomic data, metabolic data of the colon cancer patients, through which they can develop a machine learning method for better diagnosis of the colon cancer, and also hopefully for the discovery of useful biomarkers. That means the genetic biomarkers or metagenomic biomarkers or the metabolic biomarkers, and also hopefully to find the mechanism that actually leads to a certain subtype, disease subtypes, or certain or certain subtype that actually treatable by certain type of treatment. Either it is the targeted therapeutics or chemotherapy or immunological therapeutic approach, and so on and so forth. Okay. So actually, after more than 2 years, he only collected slightly over 100 samples. So that's the difficulty of collecting from clinical data, because you need to have you need to approach the right patient. Either they agree, consent with the collection of their personal data, right? Samples, and also particularly like the stool samples, and sometimes the quality of the stool samples are not good enough, and then you cannot really get the high enough quality metagenomic data. If you don't have high enough quality, the data actually is not qualified as valid data, and then you have to throw away the sample altogether. So this is the difficulty in collecting clinical data. So frequently in clinical investigations, if you want to adopt a machine learning method, so typically this particular method, random forest, is frequently used. Of course, there are some other methods, they are also popularly used. This is not the only method, but it is a more frequently used method. So that's why we want to devote some time today to discuss about the random forest model. And also, it is our, we also choose this model as the first AI we want to practice the downloading and the installation and the running of the AI model. So this is the first one. So starting from tomorrow, okay. So our question is, how when we have a smaller number of data, how can we utilize a smaller number of data to actually get a essentially to develop a model that is applicable to a broader uh, diverse group of people, right? So we encounter this same situation when we do opinion polls, right? When we do polls, essentially we can only poll a smaller number of people, but we want to essentially grasp the opinion, right, of the larger populations based on whatever the samples we got in our hand. In this situation, there's also this sampling strategy called bootstrap. Bootstrap. So it means that we grab a few people from the populations in one location or in different, essentially in different part of the society in one location, and then we resample it again in a different, maybe from different group of people and so on and so forth. And then we try to analyze the different sampling and to see if we can get a consensus opinion. So this is this kind of strategy is called bootstrap. So this is an illustration of bootstrap, the lower side. So for instance, if you have 1,000 students, we first draw a few students and to ask for their or measure their either measure their some physiological essentially the characters, right? Or of course, if we want to poll the opinion, it's the same thing. For instance, if we want to measure the height, and then we can draw a certain group, smaller group of students to measure the height, and then we to draw another group of students to measure the height. This way, we can have multiple smaller group of students with the kind of values we actually draw from the samples. And then we do this kind of we aggregate the results together and then to develop a consensus classifier. Consensus meaning that if the first, for instance, on the left side, the first classifier deemed a particular sample as a particular sample. So if the first model trained by this group of samples, the first set of samples deemed is new sample as positive, and if the second and third, the majority of them agree with each other to deem the new sample as a positive, and then we the consensus model actually make the collective decision to deem the new sample as a positive. So this is the strategy. So essentially, we draw a smaller number of samples to develop multiple models. So this way, even though our original data is not that larger than each individual model, but again, each individual model is composed of different set of different but overlapping set of samples. So we can consider them as different models. They are overlapping in samples, but they are not exactly same set of samples. So this is exactly what we want. So essentially, this is essentially follows the opinion poll strategy. Okay. Now we want to look at how a random forest model actually works. Okay. So in the beginning, right? So we have an n number of samples, m number of features. So essentially, we draw from this n number of samples a subset of samples with the same m set of features. So this way we randomly draw a number of samples smaller than n. We can generate multiple models, multiple decision tree models, right? So we can develop so many decision tree models. So now it comes to the name of random forest. So remember that each green block here represents a decision tree. So it is one tree, right? We have multiple trees, so it becomes forest, right? Multiple trees collectively is called a forest. So that's why forest name appears. Random being that we randomly, so each tree is randomly generated based on a subset of samples. So that's why it is called a random forest. So this is how the name random forest comes out. Okay. So we have this kind of random the tree called and then it forms a forest, right? Forms a forest. Okay. And each forest actually make a decision about something. Now imagine that each decision tree, remember that each decision tree focus on certain set of features. Now we revisit. If you don't remember the decision tree, we come back, right? So we can look at in this situation, the decision tree look into the email length, looks into new recipients, right? So that means a decision tree doesn't have to look into all the features. Rather, each decision tree normally focus on certain subset of features, right? So now, not only we have the choice of samples, now because we have m features, we may have the choice of selected features for a decision tree. Based on what selection of features, we can have different forests, right? So that's why you can see on the right-hand side, depending on the essentially depending on what features we zoom in, we can have different forests. So you can see a random forest that can be a very complex, really very complex forest because we can have different trees, right? Form different part of forests essentially. We can have different samples to form different part of forests, right? So it can be really colorful. You can see this is the situation, right? So the different forests, different trees, and so on and so forth. So this is the situation. In the end, we can have a very complex random forest model by selecting, grouping different samples, by selecting and grouping different features to have very colorful, high variety type of forests. So this is how a random forest model really works. So this is the example. Now comes to the second part of today's lecture. So far we talk about different machine learning classification methods. there are simple ones, right? Linear classification models, and there are more complex ones like random forest, like SVM, Bayesian models. These are all complex models. So the question is, how can we judge the performance of these AI models? So how do we do the judgment? So essentially, we go from the fundamentals. So we look at the samples. We color the samples, red being the positive sample and blue being the negative samples. We send the samples into an AI, so the AI can separate the samples into or make a prediction regarding to the label, the color of the AI, right? Sorry, the samples. Okay. There are essentially four situations. The four situations. So one situation is that we have the red samples correctly. Remember that a red sample means a positive sample. So in one situation, red samples are correctly predicted as positive. If this is the case, the prediction is actually labeled as TP. TP means true positive. So if the positive predicted as positive, this part of data is called true positive. So that's one situation. The second situation is that the negative, the blue one, is correctly predicted as negative. So this is called TN, or true negative. Negative correctly predicted as negative. So we have TP, TN. So these two situations. Now we have the third and fourth situation. So in this case, we have the blue one incorrectly predicted as positive. In this case, that blue one is labeled as FP, false positive. We have the fourth situation of the red one incorrectly predicted as negative. So this is labeled FN, or false negative. So we have four labels. Those four labels are the ones we use to measure the performance of an AI. Okay, there are multiple values to measure the performance. The first value is called sensitivity. Sensitivity means the performance, the accuracy for positive samples. So mathematically, it is simply the TP divided by the sum of TP and FN. So TP is the true positive neuron, right? FP is the false negative. So TP plus FN means all the positive samples, and then TP means those correctly predicted as positive. So essentially, it is the percentage of all the positive samples that are correctly predicted as positive. So that is the sensitivity. The second value is specificity, which is the accuracy, the performance for negative samples. So mathematically, it is Tn divided by the sum of Tn plus Fp. The Tn plus Fp is actually all the negative samples. So essentially, specificity is simply the fraction of all the negatives that are correctly predicted as the negative. So that's why it is the accuracy for negative samples. So frequently you can see publications that they actually give you the sensitivity values and specificity values. Of course, these are two values reflecting positive and negative performance. But there are also prediction performance value that actually give you the overall. That means that they combine both the positive and the negative. So this is one value, Q, overall prediction accuracy. So this is the mathematical formula. So alternative, the overall performance could also be measured by so-called Matthews correlation coefficient based on this mathematical formulation, because the overall accuracy, sorry, somehow it is actually it's lost. Because sometimes the overall prediction accuracy, so if, for instance, if you have a highly imbalanced data, for instance, the negative samples significantly outnumber the positive samples, as in the case of inhibitors and non-inhibitors. We know that non-inhibitors of a protein certainly outnumber by far margins outnumber the inhibitors of a particular target. If that is the case, the Q value may be dominated by the side with a much larger number, like the non-inhibitors. So that's why, if that's the case, people want to look into a fairer comparison of the performance, a measurement of the performance. In this case, Matthews correlation coefficient may be a better performance measurement for imbalanced data. But for balanced data, there's no problem. You can use this overall prediction accuracy. Okay. So when you read the scientific publication, you frequently encounter the AUC or ROC of AUC. So this is some kind of measurement that balance, as I mentioned, about the positive and negative performance with this imbalanced data. So essentially, it measures the variation of the positive performance with respect to the negative performance. That means that you can adjust your, for instance, as I mentioned, that if you let's take an example. So if we have a particular training set with 99% of samples as negative, non-inhibitors, for instance, with 1% of samples as positive. If we want to develop an AI model, a lazy AI can simply deem all the samples, whatever you supply, as negative, and it can easily achieve 99% accuracy, only 1% error, right? But that 1% is so critical because it constitutes 100% positive. So if you look at this imbalanced data, highly imbalanced data, you need to look at the variation of the performance if you want to focus on what happens to a particular site. ROC, essentially, ROC represents the blue line here, essentially solves the problem I just mentioned, the highly imbalanced data. So essentially, it allows you to develop multiple models by fixing the performance of the on each side. For instance, you can vary the parameters of the model to make the prediction of both these. So the y-axis represents the positive performance, and then the x-axis represents the negative performance, but in terms of the opposite, that means it is 1 minus the negative specificity. So it's right. So that means that on the y-axis, the higher the value approaching 1, the better performance. But on the x-axis, the lower value means the higher performance on the negative. So you can see that we developed the multiple models of machine learning in such a way that we want to, for instance, initially we allow the negative sample to achieve high performance at the sacrifice of the positive. That's no problem. But we want to vary the parameters to actually increase the performance of the positive, maybe or may not be at the sacrifice of the negative, right? In this case, it's really at the sacrifice of negative. So it gives you a curve of the performance. Ideally, the curve should be, we look at the lower part, right? Ideally, the curve should be the green one here. That means you can have a model at this, look at the laser light here, right? So ideally, you could have a situation, the positive achieves 100% accuracy, and the negative also achieves 100% accuracy. But in reality, you can rarely do that. So this is the normal situation, or the blue one is the normal situation. So if you want to a high performance, 100% performance of the negative, so the positive becomes so bad. But if you allow the negative performance to drop a little bit at a certain point, it can achieve both quite a high. For instance, here you can see almost 80% performance for the negative, and also 80 or 90% performance for the negative. So this is the realistic situation. So the ROC curve is almost always look like the ones, the blue illustrated here, blue ones and the orange one. But you could have a bad situation that you have a straight line here. So that means the best you can achieve is the 50% accuracy for the positive and 50% accuracy for the negative. Obviously, it's not really a good model. Okay. So here the curve here represents the ROC, or it is called the receiver operating characteristic curve. So that's the ROC. But alternatively, people look at the area under this curve. So look at the area. So frequently you can see the publication use AUC because that's easier to measure the performance of because it's closer to the what we normally familiar with. For instance, we look at this ideal case, the green one. The AUC value is actually 100%. For this normal one, the AUC value is 75%. And for this straight line, the AUC value is 50%. These are the ones we are more familiar with, rather than this ROC, because ROC is a curve without an actual value, but AUC does have a value. So 100% means the total area of this square. This square area is 100%. And then this curve is 75%. This is 50%. This is what we can understand. So that's the performance measurement of any AI model. Okay, now we have this concept of performance. Performance of AI, of course, it is one important property of any machine learning method, right? Any AI. But that's some other factors which are also very important, like the model complexity, computing time. The more complex the model is, you can imagine the more computing time. Random forest, as I showed you, it is quite complex, takes quite a computing time. But based on this random sampling strategy, somehow surprisingly, it can handle lower number of data. But of course, it can't be too low. So normally, people prefer the number of samples to be significantly over 100, at least over 100. So you can see based on the complexity level, the next complex ones are decision tree and also support vector machine. And then you have Bayes, and then this simple neural network. So here, neural network is not the deep neural network; it's the traditional simple neural network. And then we have this linear regression model. K-means are regarding to regression models, like logistic regression models. These are the topics of our subsequent lecture. Here we just focus on the classification machine learning method first. Okay, so there are some publications. Of course, when we talk about the performance, we have to ask based on what test you get the performance. So different research, different performance research actually is based on different data sets. So here is an example of the medical data sets. They use, for instance, you can see the cardiac arrest, ICU, and this kind of death, and this kind of data, and use this kind of data sets to develop and to measure the performance of machine learning models. You can see that random forest ranked first, and then you see some other models and also ranked on the upper side, like the one we talk about sorry, it's kind of support vector machines. So the performance is like 78% compared to 81% accuracy for random forest. So this shows the the kind of performance this machine learning method can achieve. Noticeably, the KN is kind of too sensitive, the laser light. Okay, so K nearest neighbor, even though it is a very simple method, it can still achieve 75%, only 5% lower than the best performing ones. Another contrast is decision tree. Without doing random sampling, in terms of the samples, in terms of the features, if you only use a decision tree alone, the best you can achieve is 73% accuracy, 7% accuracy lower than the random forest models. So that shows the power of random sampling and also the power of different selection of features. So feature selection is also very, very important. Okay. So when we talk about random forest, we mentioned the smaller number of samples. So there's always this problem. What if we only have a small data set, or sometimes they call the low data sets, low sample data sets, low sample data sets. For small data sets, so frequently we encounter, of course, you can just use brute force. I don't mind that. I don't care about the small size of the data. I just simply use the data to train the model. But frequently you encounter this overfitting problem. So what is an overfitting problem? We look at the distribution of the data on the top of the figures. All the three figures actually gives the same distribution of the positive and the negative samples. So for instance, if we can choose the blue as the positive and the red as the negative, so whatever you want. Okay. We can see that we can either draw a straight line as a border, or we can draw a better border, right? or we can draw a so-called perfect border. So there are three ways to draw border to separate the positive from the negative. Okay. In the first way, the border is very simple. It represents a simple machine learning method. We can see that we actually have a larger error, right? A larger error. We can draw a more sophisticated border, but again, we may with a few errors here. It's not perfect. Or we can force our model to be perfect, perfect separation of positive and negative. But here we realize that this border is too up to details, and then it can easily lead to errors, right? Easily, so this is definitely a overfitting situation. So that's exactly the case if we train a model with a smaller number of samples. The model can simply overfit with the data. So overfitting occurs because we have multiple as the three figures shown below. So the left side is only with one sample, and then the middle part, the middle figure is with a smaller number of samples, and then the right side with a high number of samples. We can imagine if we only have one sample, we can have any number of solutions, right? Any curve as long as it passes the sample can be regarded as a border to separate the samples, right? But if we have a few samples, we still have many choice. And this way, because of there are multiple choices, it's very difficult to find, to determine which one is the best model. So at the best, you just overfit because the model is selected. Overfitting meaning that you get a best solution for the training set, but it is far away from true solution. So that's what I mean by overfitting. That's what essentially scientific community they define overfitting, meaning that it fits perfectly only for the training samples, but it fits badly for the true samples. But as the right-hand side example shows, if you have so many samples, all the solutions tend to be the same. So that means you can, whatever solution you get, it is close to the true solution. So that's what the people mean by finding an appropriate solution that is suitable for most, at least the majority of the samples. Okay. So mathematically, a overfitting curve tends to be more complex. So mathematically, a simpler border tends to be simpler equations, as the example showed here, either a linear equation or essentially it is a quadratic type of equation. But if you have an overfitting situation, you can have many orders of the variables, and gives you a highly essentially complex equations. So that means the more complex the equations, it may not mean the best solution. It is appropriate complexity is the best one. Okay. So in some cases that, for instance, if you only have a smaller number of samples, but you want to use a sophisticated method, even deep learning method, what people can do in this situation, based on the essentially the AI communities they make several suggestions. So it may work. I have to remind you that the strategy introduced here may work for one type of data, but it may not work for all type of data. For example, let's look at this situation. It's called balanced data set with synthetic samples, or called SMOT. SMOT. In this situation, SMOT means synthetic majority oversampling technique. Okay, so in this case, we start with imbalanced data. You can see the blue samples outnumber significantly outnumber of the orange samples. We want to balance the samples to make them more or less even. How can we do that? One way is to synthesize the samples. That means synthesize the green samples based on the green samples itself. So essentially, you slightly perturb the green the yellow sample, the orange samples to add, for instance, add a random noise to generate or distort or something, or do some rotation or whatever. There are multiple strategies to synthesize a new sample, essentially the green sample. They actually more look like uh, the orange samples. So this strategy works almost very well for images. For instance, we know that in images, if we add for instance, add some smoke, it is still an image, right? If we add some fog, it is still an image. These are the essentially something that this is essentially a process that you add noise into the data, right? Or you could actually rotate the image, and then it becomes, for instance, a person upside down and so on. It is still an image, right? So there are these kind of tricks. You can actually generate many more data. They are still qualified as an image. But whether or not this strategy works for biomedicine, it is up to debate. So you may try it. For instance, if you have genetic data, what if you perturb, for instance, you have gene expression data, transcription data. Can you perturb the expression level of certain genes, and then you generate a new sample? Is that a new sample really qualified as a new sample? We know that certain genes, they may not, the expression level may not go beyond a certain value. Some genes may be kept silent at all, right? So of course there are this kind of debate, but here, debate aside, I'm just telling you what the AI community deal with the case of small data set. This is one strategy, smart strategy. Of course, you can up samples. That means you can add synthetic samples. Of course, you can do the opposite. You can downside the sample of higher numbers as the lower figures illustrates for the gray samples. You can actually randomly select a subset of gray sample to make it almost even in terms of the number of samples. So this is also a suggestion made by the IT, by the AI communities. Okay. There are also some other strategies. I think because of the nature of our lecture, we will not go into too much details. I just tell you these two type of strategies. Okay. Now I conclude today's lecture. So maybe it is time for your questions.
Okay, thank you very much, Professor Chen. So let me see if we have questions in the chat box. Meanwhile, I will request our in-person audience, if you have any question, please, the floor is open. Is there any question for Professor Chen here? Okay, so let me read some of the questions posted in the chat box. Okay, so one is the question from Mr. Ahmed Hafiz. He's asking, how do we decide sample number less than in bagging process, less than n in bagging process?
Oh, that's a very good question. So it is again depending on your decision tree model, okay? Because remember that each individual model in the random forest is a decision tree. A decision tree also depends on how many features you choose to develop the decision tree model. The more features, the more complex the decision tree model is. It requires more samples. For instance, if you only choose very few number of features to develop your decision tree models, of course, the sample can be smaller. So it is there's no fixed number of samples. So essentially, it is up to you to try. So, but the general guidelines that whatever model you use, if possible, you want the number of samples to be over 100, even for a decision tree model. But if it can't be achieved, you may try, for instance, if you only have 100 samples, you may try at least 30 samples per decision tree model, or 50 or 60 or something like that. So you just need to try. Also, this is now this question is really actually it touched the heart of AI. So I remember that there's a news with a journalist interviewing Google executive, asking about what, because they developed AlphaGo, right? So essentially, so they actually ask the executive, what is AI? So the answer is 3 words: wait, wait, wait. Because AI is essentially all those parameters. The weights in deep learning translates to the parameters. Weights is the parameters of deep learning. When it translates into random forest decision tree, it is in terms of
Okay, thank you very much, Professor Chen. So I think just one last question that I can see. It is from Mr. Hamas Ashraf. He's asking that I don't know what he's referring to, would that not count as forgery of the data set? AI also does that. So let me take another question. Okay. How many instances will be there for oversampling and undersampling, and any specific count of class which can tell oversampling or undersampling? Okay, Dr. Chen, your mic is mute. Your mic is mute.
Oh, that's why. So you can't hear me, right? So
Yes.
In my answer for last question, was it mute or it is on?
No, it was mute. So maybe you can start from the beginning for the second question.
So the last question, right?
Yes.
So actually, in the last question, the question is regarding to how many samples are good enough. So what is out of n samples, how many samples are needed to train the random forest model? So essentially, it depends on the decision tree because each random forest model, each element of the random forest model is a decision tree. So it depends on how much sample you need to train a decision tree, right? So so this again is depends on the which features, how many features you use to train a decision tree. The more features you use, it requires more samples. Okay, if you use only a few features, you may need quite a small number of samples to train each individual decision tree. The general guidelines that when you train a decision tree or whatever model, the general guidelines that it's better to use over 100 samples. But if you only have 100 samples for training a random forest model, then you have no choice but try a fewer number of samples, maybe 30 or 40 or 50, at most 60. These are the kind of thing you can try. And also regarding to how much percentage of the samples to train each individual decision tree, again, there's no general rule. You simply have to try. So this touch the heart of AI. By touch the heart of AI, I mean that when you develop an AI model, what is the essential thing you normally deal with? It's essentially, so I give an example of that's reported in the news. So a journalist interviewed an executive of Google asking what is AI. So the answer is 3 words: weight, weight, weight. Weight is the parameters of a deep learning model. For decision tree, the parameters are which features to choose, how many samples you use to train the decision tree, right? Remember the decision tree, you need to know the exact features in order to decide the branch. So these are the parameters, but there's no answer so you have to keep trying. You have to be patient. So that's why the executive answered, wait, 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 because you have to try to determine which are the best weights, best parameters. So that's the answer for the last question. Okay.
Thank you very much, Professor Chen, for your time and a wonderful lecture, Professor Chen. There are many participants who are asking about your slides of your lecture. So is it possible? And if you allow, we can share it with our participants.
Sure, sure. Why not? Yeah.
Yeah,
So
so
I also frequently update the lecture slides, and I will send you the updated one, and you help me to update to the website and also to do the distribution. No problem.
Yeah,
Okay.
thank you very much. And I would also like to announce here that from tomorrow, Professor Chen and one of the facilitator, Dr. Wang, they will be covering some of the practical sessions. So to do some of the pre-installation, we have arranged a pre-installation session for all the in-person and online participants. So what we know so far is that you have to, for the in-person participants and also for the virtual participants, I have posted a link that is www.anaconda.com. You have to go there and you have to download this whole suite. And we will have 2 technical facilitators in person here. One, Dr. Alito Basum, who has joined here in person as a participant. He's also a faculty of University of Computer and Emerging Sciences. And we will also have Dr. Sadia joining us tomorrow, and both of them will help you to do the pre-installation. However, it is recommended that you do pre-installation at your home, because if everybody is here and pre-installing and downloading the suite, the internet speed may go down. So you please go to your home, go on this website and download this whole suite. And if you have any issues, we will do the pre-installation session here, and you will have the technical facilitator to help you if you have any problem with the downloading or executing the suite. Additionally, the timings for this pre-installation is from 12:45, which is around 45 minutes before Dr. Wang's lecture start at 1:30. So first we will do all the pre-installation, and that is both for the in-person and as well as for the online audience. And once you are done, then at 1:30 p.m., as decided earlier, Professor Chen will continue his lecture, and maybe you can do some hands-on practice. For the online participants, for the pre-installation, please use the same Zoom link that we have provided, and this link will start at 12:45. And the lecture of Professor Chen will be from 1:30 onward for 1 hour. So I hope everything is clear. And thank you very much. And we hope to see you at 12:45 tomorrow. Professor
Okay,
Chen,
thank
see you
you.
tomorrow,
See
inshallah,
you
at 1:30.
tomorrow. Okay.
Thank you very
Okay.
much. Thank you. Bye-bye.
Thank you. Bye-bye.